Okay. Hopefully that if you found the 5-1 homework pretty reasonable, which again was u prime over u over and over and over again with a couple little twists, this shouldn't be that bad. Okay, so we're going to talk about the opposite of what we did already. We did derivatives. Now we're going to do integrals, okay, of the natural log function. We're talking about the log rule for integration. I said that already. We're going to talk about trigonometric functions. So we've done some integrals of trig functions, sine, cosine, but then we had all these bizarre ones, like what's the integral of secant tangent? What's the integral of negative cotangent cosecant? And they were just the reverse of the first 6. But what we're going to learn about today is what actually is the antiderivative of tangent, or the other 4 that we haven't talked about, tangent, cotangent, secant, cosecant, and how to do that. Because now we have the techniques that will allow us to do that. And then, of course, you should be able to make some really good grilled cheese. Anybody grilled cheese fan? No? Yes? Yeah, do you make a lot of grilled cheese?
Not really.
No? Okay. Do you always use the same cheese, or do you branch out?
Just whatever's in the fridge.
Whatever's in the fridge. Do you ever add anything to it, like, I don't know, pulled pork or?
Sometimes.
Yeah, so, okay, all right. Anybody at home, grilled cheese fan? Amanda, I see you smiling. Big grilled cheese fan? No? You'll take it or leave it, right? Okay, all right, good. Okay, so here we go. We did this already, and today we're going to also have to address the idea of this absolute value bar that showed up sneakily at the end of the 5-1 lesson. I'm going to throw it in here because we need it. You'll recall that you cannot take the natural log of 0 or a negative number, so the absolute value bar guarantees that we don't make that mistake. Okay. And it becomes relevant in a second. This is all review. You know this. That's 5-1. So using a little bit of calculus logic, if we wanted an integral, we could just reverse what we've done. Okay, so we get that. And we talked about this a little bit. In fact, this is where we talked about where the natural log comes from. The integral of 1 over x is the natural log of the absolute value of x. So now all of a sudden, those absolute value bars become very important. So again, when we did derivatives, if we put a negative number in there, it just wouldn't work because we can't take the natural log of a negative number. Going backwards, you'll notice that in the original problem, 1 over x, I could put -3 in there, for instance, but it's going to cause problems when we take the integral. So you will need to get in the habit of including those absolute value bars. The thought is this: it's always better to have them and not need them than to need them and not have them. Okay, so just put them in there. And we'll talk a little bit more about this when I get into my examples here. Okay, questions? So far, we're good? Everybody got this? Okay, so we start with something really simple. This is the same thing as 2 times the integral of 1 over x dx, which is 2 times the natural log of the absolute value of x plus c. And then if I wanted to get all fancies in my pantsies, I could do this. Question: where did the absolute value bars go?
You're squaring it so you don't need them.
Can you say that louder so they can hear you?
You square it so you don't need them, because when you square something, it becomes positive.
Good. Did all of you hear her at home? The Zoomers? Okay, good. However, this wouldn't be wrong. Okay. Or even if you wanted to do it over here, you could do it there too. Okay, that's not wrong. So like I said, you're better off leaving it in there and not needing it than to need it and not leave it in there. Okay. So easiest of examples, no problem. And that's a paragraph explaining what, what's her name? Paige just told us. Okay, what's her name? Sorry. Yeah, whatever. Okay. So you'll see the title of this slide says common mistake. So what people do is they start to get in the habit of 1 over anything. The integral of 1 over anything is just going to be the natural log of the absolute value of that anything. So people will just say, okay, well, this is the natural log of the absolute value of 2x minus 5 plus c. And that would be wrong. What's in the bag?
Oh, clay for my project.
You building a house or something?
No, I'm doing a reduction sculpture.
Oh, I don't know what that means, so I'll just smile and continue on with my lesson. Okay, so that would be wrong. Why is it wrong? Because it has to be done as a u-du problem. So let me change colors and show you how it's supposed to happen. U is equal to 2x minus 5. du is equal to 2 dx. So dx is equal to 1/2 du, which makes this 1/2 times the integral of 1 over u du, which then becomes 1/2 times the natural log of the absolute value of u plus c, which is 1/2 times the natural log of the absolute value of 2x minus 5 plus c. And you'll notice the difference between those two things. That pesky little 1/2. Okay? And again, that will happen repeatedly because you'll get in the habit of seeing 1 over anything and just taking a natural log. You do still have to do it as a u-du problem. Okay. Questions? Good? Next example. This doesn't even seem like something we've talked about, but if we start doing this, let's see, Bethany, what would you choose u to be?
X to the 4th plus 3x.
Bingo. Well, look at that. This becomes the integral of 1 over u du, which is the natural log of the absolute value of u plus c, which is the natural log of the absolute value of x to the 4th plus 3x plus c. And I'm not even going to play the game to figure out whether or not that stuff can always be positive, which would allow me to drop the absolute value bar. So I'm just going to leave it there and forget about it and move on. Okay? So a problem that becomes a u-du right away doesn't even seem like it would be a natural log problem, but of course, as we start to do the problem and we get down to that integral of 1 over u, we realize that yes, that is going to give us a natural log of an absolute value type answer. Okay, fairly easy, yes? Yes, easy, 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 easy at home, yes? No problems? Okay. It doesn't get any more difficult. This is it. I'm not trying to lull you into a false sense of security. Okay. So if we move on, what happens now is we just learn to try different things. Okay, so for instance, I get this guy. Now, obviously that's not something I can just grind out because it's a quotient, and quotients, we have no quotient rule for integrals. At this point, I would hope that you would also realize that that's not a u-du problem. The reason it's not a u-du problem is the degree of the numerator is the same as the degree of the denominator. So if I choose the numerator or denominator to be u, things are going to cancel properly. So I have to figure out a different way to do it, and the way I'm going to do it is split the fractions. Okay? I think I have this worked out already in my slideshow. Yeah. Okay. So, whoops. Sorry, I guess I don't. Splitting the fraction gives me x squared plus 1, nope, plus x plus 1 over x squared. What am I doing? I'm not doing anything right. Hold on. Starting over. Split the numerators. I get x squared over x squared plus 1 plus x over x squared plus 1. Whoops. dx dx plus the integral of 1 over x squared plus 1 dx. Okay. Now what? Is it safe to assume that you could do this? Yeah? Okay. And that's what we talked about already. Is it safe to assume you could do this? Okay. What about this guy? That's going to cause some problems, isn't it? How do we handle that? By the way, how are you going to do this last one?
You just bring the denominator to the numerator.
Yeah, but then it generates a quotient rule, or a chain rule, right? I could write that as x. So what you're saying is write that as x squared plus 1 to the negative 1 power?
Yeah.
Yeah, but then we have a chain rule, and chain rules don't work.
Or, I mean, couldn't you just like bring it up as like x to the negative second power?
Ooh, no, 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 no,
Just multiply it out?
no. You got a plus sign in there.
Oh, okay.
Okay? So, are we all good there? Let's start with the easy one. That would be a u du, right? Choose u to be x squared plus 1, and then the derivative of x squared is 2x, so the x's will cancel, and we're good to go there. This one, there's a problem there, and there's a problem here. Okay, so how do we handle this? Well, here's a trick that you can use. I'm going to start over with this whole thing. And the reason I'm starting over is because after I split the fraction, you see that 2 of the 3 don't work. So is there a different way to approach the problem? Well, I'm still going to split the fraction. I'm just going to do it in a sneakier way. What if I split the fraction like this? So instead of creating 3 different integrals, I'm just going to split it into 2 integrals. I'm going to pair this x squared plus, or x squared and the 1 together to get this x squared plus 1. This we talked about already. You can do that, right? That's a u du. And this just becomes the integral of dx. Sure. Which is why I chose this as an example, because now you know. Okay, you can take chunks of that sum in the top and pair them up any way you want. I could have done x squared plus x, and then done 1. I could have done x plus 1 and the x squared. But again, as you start to break it down, the first thing I would do is try to break it down into 3 different integrals and see if they work out nicely. If they don't, then you've got to try different things. Okay, and again, u in this case would be x squared plus 1. All right, does that make sense? This is just another tool that you can use when you get to something that you know is not going to work out nicely. And as reiterating what I said before, the reason I know it's not going to work out nicely is because the numerator and the denominator have the same degree. Unlike the one we did previously where the numerator and denominator are off by a degree of 1, that you start to see as a nice easy u du. This one requires a little bit of sneakiness. Okay? Questions? Okay so far? That's going to take some practice, no doubt about it.
Mr. Reedy?
Yes?
I'm a little confused, like, why you can split up the numerator like that.
Are you good with this idea? If I have a plus b over c, are you good with the idea that that's a over c plus b over c?
Yeah, I think I just really, yeah, definitely.
I mean, think of it as the reverse of adding fractions, right? 1/5 plus 3/5. Whoops. 3/5. I have trouble with numbers, sorry. 3/5 is equal to 1 plus 3/5. Okay, so what I'm doing is just going backwards. The same is true if I'm adding three fractions. If I'm adding 1/5 plus 3/5 plus 4/5, that's the same thing as 1 plus 3 plus 4 all over 5. And I'm just going backwards and choosing to split it up. So I could rewrite this. Let me change colors here. I could rewrite this as 1 plus 3 over 5 plus 4 over 5.
Okay.
Now, does that make sense?
Yeah.
Yeah. And so that's what I chose to use. This is what I chose to use to solve this problem. I kept two of those numerators together so things canceled nicely. Okay?
Okay.
Go.
So what happens to the integral of dx?
This one?
No, on the like.
Oh, in general.
Yeah.
Goes away.
That's nothing.
This guy, way back when we first introduced integrals, are you talking about this guy? I'm sorry.
Yeah. Like,
Oh, okay, good. I get it now. Okay, so this is, one way to think of it is think of that as 1x.
Okay.
The integral of 1 would just be x. So this would be x plus c.
Okay.
And what am I trying to say? The thing that I do in my brain, which I don't know if that's really where you want to go, but I always ask myself, does that make sense from a derivative standpoint? So if you're shaky on integrals, switch your thinking. When I get that answer, I'm asking myself, does that make sense from a derivative standpoint? Well, what's a derivative of x? It's just 1, and I'm good to go.
Okay.
Okay? Any other questions before we move on? For some reason, this differential equation shows up all the time. I don't know why, but it just does. This 1 over x plus natural log of x. So I'm going to show you how to solve the problem. However, you might just want to use the formula at the end of this. Okay? So remember, solving a differential equation, I'm working backwards to figure out what the function is that generated that derivative. So I want to take the integral of x times 1 over x times the natural log of x. And by the way, this is not the natural log of the absolute value of x natural log of x. Okay, you can't just take 1 over something and say the natural log. This is bad. We're going to have to do it a different way. Okay, so to do that, I'm going to choose, it's here somewhere. Here we go. I'm going to choose u to be the natural log of x. Therefore, u prime is 1 over x. And we do a bunch of work there to simplify. So u is the natural log of x, du is 1 over x, move the x to the other side, and hopefully you start to see what happens. Now that x with the du is going to cancel with the x on the bottom, and after all this gunk, it reduces to something pretty like 1 over u. And the integral of 1 over u is the natural log of the absolute value of u, and then you sub it back in. And we get this weird inception thing that will come up on the day 50 homework, because I know you did a problem like that on the day 50 homework, taking a derivative. So it ends up generating a natural log inside another natural log. And the reason I did this is twofold. Number one, it comes up a lot for some reason. And number two, it shows you this whole process that you're going through over and over again with some weird results, this natural log of a natural log. Excuse me, not COVID. So as I said, if you want to go through the process to take that antiderivative, you can, or you can simply write down that formula because it does pop up a lot. Whatever works for you. Some of you are memorizers. Some of you are applicationists, if that's a real word. It's entirely up to you. Excuse me. Okay. Now let's get to something interesting. What about that pesky tangent, secant, cosecant, and cotangent? Okay. We have not done this yet. We've taken the derivative of tangent, but we haven't done the integral of tangent. We've had sine and cosine and then 4 other bizarre ones that fit into this nice little niche. We just want to take the antiderivative of something real basic like tangent. Okay, well, how do you do it? The reason we're doing it now is because we haven't had the tools to do it up until this point. So I'm going to start by rewriting the tangent as sine over cosine. Now, we've done some integrals of sine times cosine. This is the first time we're doing the integral of sine over cosine. All right, Kev, pressure on you. No pun intended. Would you like u, not you, but you, the letter u, to be sine or cosine? Cosine. All right. Derivative of cosine is? Negative sine. Whoops. Madison, did he choose wisely?
Yes.
He did. Very good. How do we know? Well, that's going to cancel with this. So this becomes the opposite. I don't know what just happened there. No, wrong way. No!
It becomes 1 over u.
Yeah, hold on. I'm experiencing technical difficulties. 1 second. No, bad. There. I can do this. Negative. There it is. Okay. That cancels with... I'm an idiot. 1 over u du. That's a d. Sorry, I got flustered there for a second. Which is the opposite of the natural log of the absolute value of u plus c. Running out of space, so we'll bring this over here. Sub it back in, the natural log of the absolute value of the cosine of x plus c. Good job, Kev. There's the antiderivative of tangent. And hopefully, you now understand how we could do secant. Okay, so if I wanted to do the antiderivative of secant of x dx, we would rewrite this as the antiderivative of 1 over the sine of x dx. Oh, I lied. Come on, Rita, you're better than this. You can tell it's Monday. Yeah, secant is 1 over cosine. But I saved you all that hassles and given you this nice pretty little chart. Blah, 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 blah. Did that already. There you go. There's all 6 trig functions. You knew the first 2. The other 4, though, are a little nasty. And yes, those absolute value bars are muy importante. And of course, I disagree with the last. I changed my mind after I said this. You won't have to memorize because it's open notes. Just make sure you have them written down correctly. All right, everybody good? Got them all down? Yep. Zoomers, got it all? If not, it's in your book. You can find it in your book, but should have had plenty of time.